Shop the Plato's Closet Black Friday event in North Charleston and West Ashley and let the deals begin. You know Plato's Closet always has a huge selection of trendy recycled styles at amazing prices, but Black Friday deals are different. They're better. We've been holding back some of our best inventory, and you won't want to miss our Black Friday event. Save on gently used styles from Patagonia, Lululemon, Lilly Pulitzer, and hundreds of popular brands. Plato's Closet is ready to let the Black Friday deals begin. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
Hello and welcome to a new episode of Space Nuts. My name is Andrew Dunkley, your host. It's so good to have your company. And being episode 345, we dedicate the entire show to questions from the audience. And we're going to do a bit of a mix of audio and text questions today. We'll fit in as many as we can. We've got 500 of them here. We might get two or three. We'll see how we go. We'll be looking at the rotation curve of galaxies and walking on neutron stars. We'll also be chasing up the previous episode's talk on asteroids, dark matter, dark energy, white holes, the period of inflation, and much, much more coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to answer all of those questions and more is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. It's great to see you again.
You too.
After so long.
It's been so long.
Yeah.
Been so very long. Tongue in cheek. We should just blow the whistle. We're doing catch-up episodes because you're going to be away for a bit and I'm going to be away for a bit. Adds up to a long period of time where we won't be able to record, so we're working ahead of time. But for you who are listening, it is at the right time anyway, so it doesn't really matter that I'm explaining that like I am. We might as well get stuck straight into it because we've got a lot to do. So we will just go straight into question one, which comes from Rusty in our favourite WA town of Donnybrook.
Hey, Fred and Andrew, it's Rusty in Donnybrook. I hope you are keeping cool in our extended summertime here in Australia. Fred, you once famously remarked on this show that spiral galaxies, when viewed in infrared light, completely lose their spirals. You don't see them at all in infrared. And so I'm wondering, since most of the visible light is from the spirals, and almost all of the ultraviolet light is also from the spirals, how does the rotation curve vary with wavelength? Thank you.
All right. Thank you, Rusty. Nice to hear from you, one of our regulars. We did talk about that before, and it became apparent that when you view a spiral galaxy through infrared, there are no spirals. And, it's got Rusty thinking. Rusty has an interesting mind. He thinks about a lot of things.
Yeah, and actually, Andrew and Rusty, what's given the lie to my comment about the spiral arms disappearing in the infrared is some beautiful James Webb Space Telescope images of galaxies.
Wow.
which have sensational spiral arms.
Okay.
But you're seeing... what I said originally is that if you look in the infrared, you're seeing galaxies dominated by old stars, and they tend to be yellowish in color rather than blue and white as the young stars are, and so they do, and it is true that the galaxy itself has this underlying population of these elderly stars that have been there a long time.
Like you, Fred, you're an elderly star.
Well, yes. No, I'm just old, Andrew. There's no bitting about the bush. In fact, bordering on ancient, I think I could say. So there's an underlying population of old stars, including me, and and they tend not to delineate the spiral arms. Then, if you look, most images of galaxies, and particularly the early black and white ones, which were sensitive to the blue, actually, rather than the red.
Yeah.
They show the spiral arms because that's where the young energetic stars are. They're white or bluish in color, and they show up. Now, spiral arms are, we know, the location of many young stars because the spiral arms are caused by sound waves effectively passing through them and basically sparking them into ignition, and so you get short-lived, very bright stars which show up as bluish objects in the spiral arms. Now, why does the James Webb Space Telescope show galaxies with lovely spiral arms? And the answer is that what you're seeing there is the dust in these spiral arms, predominantly the dust, and that dust is being also pushed into a spiral shape by the shock wave, the density wave that's passing through them and causing the star formation that reveals the spiral arms, the stars themselves, the bright stars.
Right.
So that's just by way of a caveat to what I said, as Rusty quoted me as famously having said that the spiral arms disappear. And it's still true, but it's certain wavelengths of light, which brings me to Rusty's question. How do the rotation curves vary with wavelength? So if you are always looking at stars, you're going to see, you're seeing objects whose spectrum is going from often the ultraviolet to the infrared, but it's the same object. And so it's the same moving with the same velocity.
Yeah.
So in that regard, looking at stars in different wave bands, you're still going to see the same velocities. But it extends even further than that. And that is because, and this was actually some of the work that Ken Freeman here in Australia and Vera Rubin did in the United States back in the 70s, demonstrating the rotation curves of galaxies are flat. They don't behave as you would expect. If you look at clouds of gas with radio telescopes, the sort of, cold hydrogen in space, which emits its radiation at 21 centimeters, it's in the radio spectrum. That follows the same rotation curve as the stars do. So in that regard, the rotation curves are independent of wavelength.
Aha. Okay. Very good. That was simple.
Yeah, long answer to a short question. But a good question, Rusty. As Andrew says, you always think outside the box.
You do indeed. Thanks, Rusty. And now we'll move on to North Carolina, which is a long, long way from Donnybrook. And one of our female listeners, we don't get too many questions from our female listeners, so it's nice when we do. Hello, Nan. I'm confused about gravity, she says. You'd be the only one. I heard it described as the curving of space due to the mass of an object. Thus, an object in the vicinity of another object falls into the curve, causing the object to follow the curve. When referring to the formation of stars, the description seems to be that the gas is squeezed until it becomes hot enough to ignite. This is also described as gravity acting on the gas. That seems to be a different action of gravity than the bending of space. Help me understand. Thanks, Nan.
What a great question. Yeah, that's a fabulous question. So, yes, it was Einstein who said that that gravity is the phenomenon. It's a geometrical phenomenon, is what he said. It's actually about space being bent by any mass that's within it, and so and that's fairly easy to get your head around for something like the sun, where you've got this giant ball of gas which is gravitationally distorting the space around it, and that's demonstrated by the fact that when you look at the sun in eclipse, you see stars in the background looking to be in the wrong direction, which is how they proved that Einstein's theory was correct. But it's probably less easy to get your head around that when you're thinking just of a giant cloud of gas. So if you've got a blob of gas in space, and that gas is gravitating because it's made of matter, then even though it's pretty tenuous, is that the word? Yeah. It's a tenuous object. It's not solid like a planet. It will still distort the space around it, and the effect of that is, once again, that the outer edges of that space will be bent less than the regions towards the center where the mass is concentrated, and you'll get this compression effect. The gas will slide down the bent space, and the effect of it is the temperature increasing, and eventually that cloud of gas turns into a star. It's the mantra is that what is it? Matter tells space how to bend. Space tells matter how to move.
Right.
That's the, and I can't think it might be John Wheeler who said that.
Okay.
Decades ago, but that's the bottom line.
Very clever. Okay. Gee, we're getting through them fast.
Are we?
Yeah, we need to slow down. It's just too quick for my brain.
We can easily
Indeed.
slow.
Thank you, Nan. Let's go to our next questioner. And this one's a sort of a speculator from Russ.
Hi, guys. Love the show. It's Russ here from Stourbridge in the UK. My question is more of a journey that we could take. Let's take out the physics of the impossible, i.e. we won't be able to do it, but let's have a walk across the surface of a neutron star. What would we be seeing on the surface? What would the surface look like? Would it be glowing? Would it be white? Would it be iridescent? What sort of colours would we be seeing? If we bent down and touched the surface, what would it feel like? If we were able to jump off a little step, maybe a foot high, how fast would we be going when we hit the surface? If we looked up into space, what would we see? Can we just have a theoretical walk across the surface of a neutron star? Thanks very much. Love the show, guys. Take care.
Okay. Thank you, Russ. We have talked about neutron stars before. I think the very first thing that we can say is as soon as you walk on a neutron star, you're a mountain climber.
Yeah, because the mountains are, as we discussed before, millimeters high.
Yeah.
A few millimeters. Actually, something happens to you before that, though.
You die of a horrible, painful, immediate, crispy death.
Well, you're spaghettified.
Oh, right.
Just like a black hole, the gradient, the gravity gradient around a neutron star is very steep. So your head's feeling, as you walk, your head is feeling less gravity than your feet, and you're spaghettified, basically. Yeah. It's not very nice.
Not pretty.
But yeah, what an interesting question. And I think, and I ought to check this, but I think the surface of a neutron star is very, very radiative. So it's beaming out light, and I think it's probably ultraviolet because it's such high energy.
So it's all the good stuff that the human body loves.
Exactly. Yeah, well, you've got now everything else. You've got everything. It's not just the gravity and the blinding intensity of the radiation. You've also got intense magnetic fields that'll probably screw your insides up completely. Stepping off a doorstep wouldn't happen because the doorstep's already been squashed as being something less than a micron high.
Fair enough.
So there's not much to do there. Looking at the sky from the neutron star, you would see, it probably would look a bit weird because there would be definitely gravitational distortion effects in the space around you. And that might cause some strange effects, particularly near your horizon, with stars compressed one way or the other. So it would be an environment that is very, very different. Assuming that we could magically somehow survive it.
Yeah,
it would be very, very different from anything we experience on Earth, and that is, I guess, typical of astronomy. All the objects we talk about, if you transported yourself from Earth to one of those objects, no matter what it was, even if it's an asteroid, the phenomena that you would encounter will be so different from what we have on our own planet that it makes for very interesting thought experiments and very interesting reading, and I hope very interesting podcasts.
Indeed. In fact, we are so well adjusted to our own planet because we've spent hundreds of thousands or tens of thousands of years adapting to this environment. Just about anywhere else we could go would not be good for us.
No, that's right. And
unless we could find another planet exactly the same as ours in terms of
every
size
way.
and
Yeah,
proximity.
in every way.
Yeah.
Well, it's, I'm going around a star like the sun rather than a red dwarf that's going to spit out solar
Radiation.
flares all the time. Yes. No, I mean, it's not surprising. We've evolved as creatures of the Earth, so we are very well adapted to it. And you can kind of imagine how many million years it might take for humans to adapt to being on a neutron star if they could.
Yes, I think supermodels would adapt well because they like being skinny.
Yeah, skinny is one thing, but spaghettification is another. The one good thing about a neutron star is that you could walk all the way around it in a matter of hours.
Is that right? Because they're not very big, are they?
The side of a city, that's right.
Yeah.
So, yeah.
Yeah, as long as you don't...
30, it might be 30 kilometres.
As long as you don't get hit by a bus or get mugged. Probably get mugged.
A neutron bus. Oh, yeah.
All right. Thank you, Russ. Lovely to hear from you. And thanks to Rusty and Nan for sending in questions to us on this episode 345 of Space Nuts.
Roger, you're loud and clear here also.
Space Nuts.
All right, we'll just carry right on, Fred, because we have a question from Jeff. This is a follow-up to something we talked about in the last episode.
Hey, Fred and Andrew. Jeff in Ohio, USA here. Hey, just wanted to clarify a couple of biochemical things from the Uracil and asteroid discussion and ask a question as well about dark matter or dark energy. So, yes, biological processes on Earth that make proteins use all L amino acids, but some biological organisms actually use D amino acids, make D amino acids. For example, anthrax makes a polymer out of glutamic acid that's all D or mostly D. And also, we're talking about trying to find DNA on an asteroid. There's a leading hypothesis that actually RNA was the world before DNA and protein showed up, that it not only held the genetic material like DNA does, but also catalyzed reactions like proteins do. And we still see evidence of that today. So my question about dark matter, dark energy, I'm slightly familiar with these two concepts being described as a web that kind of holds galaxies together and keeps them from flying apart. And I think there was some kind of modeling that showed that, or at least tried to model what that web might look like maybe a few years ago in Science or Nature. Could you talk a little bit more about the background on this dark energy, dark matter web? I'd like to know a little bit more on the background so I can kind of run with it from there. Thanks, you guys. Keep up the good work. Really love the show.
Thank
Jeff
you.
out.
Thank you, Jeff. And wow, what an astute fellow. He knows his stuff about RNA and DNA and, it's very, very clever. Brought up some interesting points. I didn't, is he right that the Earth was probably more RNA than DNA in the beginning and something changed?
I'm not sufficiently engaged with the world of evolutionary biology to know the answer to that.
No, I haven't heard that before.
I'm very glad that Jeff put those ideas there because, we'll follow up on that and find out what the story is there.
But his main question was about one of our favourite topics, dark energy and dark matter. And, he did describe them as the web that holds galaxies together. And we have said before that if there was none of this, galaxies would just spin themselves into oblivion. They'd just go in all directions, I suppose.
Wow.
So, how does it work, I suppose, was what he wanted to know.
Yeah, so...
giant space spiders.
God, you've cut to the chase straight away.
David Bowie was right. Spiders from Mars. There you are.
Spiders from Mars, yeah. So we need to disentangle dark matter and dark energy, though, because dark energy is not something that's part of the web that Jeff's talking about. Jeff's talking about the cosmic web, which is structures of matter within the universe. Now, those structures of matter, we think, were instrumental in the creation, just as you've said, Andrew, of galaxies, because we find that when you build models of the way the Big Bang evolves, you end up with this web of material. It's almost like a foam, if I can put it that way, very much like cells of a honeycomb, with the walls between the honeycomb forming the structure of the web, which is there in both dark matter and normal matter. The dark matter probably was the first thing that to sort of crystallize into this web shape after the Big Bang, with the normal matter being gravitationally attracted to it, because dark matter outweighs normal matter by 5 to 1 or thereabouts. So that's the hydrogen that followed the dark matter, and that hydrogen then collapsing into stars, gas clouds, galaxies, and all the stuff that we're familiar with now. But dark energy is probably uniform throughout the universe. So it's not part of this web structure. The web structure is just for matter, whether it's dark matter or what we call baryonic matter, which is the matter that we can detect. That forms the web, but dark energy doesn't. Dark energy seems to be a property of space itself. Irrespective of what structures you build inside it, the dark energy is there. And the effect of dark energy, of course, is what we see with the universe accelerating in its expansion, as it has been doing for about the last 5 billion years. We think that before that, it wasn't accelerating in its expansion, even though dark energy was there.
Yeah.
But the galaxies were close enough together that their mutual gravitational attraction resisted the effect of dark energy. And it was only as the universe continued to expand that the galaxies became far enough apart that their gravitational pull towards each other was not strong enough to overcome the accelerating effect of the dark energy. So that acceleration is something we've only seen for about, half the age of the universe. Before that, the universe's expansion was probably slowing down.
And any theories as to what changed?
The fact that the galaxies became far enough apart that the gravitational pull between them wasn't breaking the expansion,
right?
And so that allowed the dark energy to become the dominant force.
We were basically holding it back until it reached a release point, and away she went.
Right.
Yeah,
where she went, quite gradually, but
it's sort of like when you blow up a balloon. When you first start to blow up a balloon, it's a hard thing to do, and then it suddenly gets easier.
That's a really good analog, actually, because what you're feeling at first when you're puffing hard against the resistance of the the rubber or whatever material it is, and that then gets beyond a certain point where it's really easy to blow it up, and if you do it too much, it bursts.
Yep.
Which is probably what the universe will do in the Big Rip in a few trillion years' time,
or next week, whichever is longer,
whichever comes sooner. Yes, that's right. Yeah. Well, I hope that explains or helps to explain some of the confusion there, Jeff. Separate dark energy and dark matter out in your mind, because they're quite different things. But the dark matter is what forms that web-like structure that basically is the scaffolding on which the objects in the universe were built.
Yes, and as we've mentioned in previous episodes, they're just badly named. Dark energy should probably be called something else so that there's no confusion, but that's where people get sort of crossed up.
Dark matter would have been better as invisible matter, I think.
Yeah.
But dark seems to be the buzzword in astrophysics.
It does, yeah.
Yeah.
All right, thank you, Jeff. We got a text question from Austin, Texas. It's Carlos. He says, "Hello, Andrew and Professor Watson. I will preface this question by saying that it may not have a conclusive answer because it details in the theoretical. I was pondering the concept of white holes being mathematically understood but not observed. I wonder if white holes could lurk in the dark matter spectrum of the universe. Just like we can't detect or understand dark matter / dark energy, could it be possible that white holes exist within this yet to be understood spectrum of the universe? Thanks for a great show every week. Much love to y'all." I hope I said that right, from Texas. Yeehaw! That's what not me, him.
Good. Well, that's good. That's very flavoursome and
It is,
authentic.
yes.
And there's some boot scooters lurking somewhere in the
There are,
background.
probably.
There as well, I think. Yeah, so that's an interesting thought. Let's explore that a little bit. The idea that maybe in the dark matter universe, which we can't detect directly, there are objects akin to black holes and white holes. Let's do it both ways.
Okay.
And Carlos is absolutely right that the mathematics of black holes or the mathematics of gravitation let you conjecture that there are such things as white holes. And when you're working in the equations, I think what you do is you reverse the sign of time. So you put times going negative, and you got a white hole instead of a black hole. But we see nothing in the universe that actually could be one of those, because unlike a black hole where nothing gets out, with a white hole nothing gets in.
Yeah.
And you'd think you'd notice that. But I guess the bottom line here is all right, let's think about dark matter. We think it is some kind of species of subatomic particle, and perhaps many different species of subatomic particle, which doesn't interact with normal particles, so it doesn't interact with light. We can't see it shining. It doesn't interact with matter. It doesn't seem to react with normal matter. All it does is displays gravity. It has gravity, and that's how we detect it. Because, exactly as you said earlier on, when we look at the way galaxies work, if you spot a rotating galaxy, and if all that was in there is all that you can see, if that's all there is, then it should have flown itself apart. Gazillion years ago, maybe only millennia ago, but a long time ago. It can't exist without the idea that there is some invisible material holding it together. And when you do the theory, you get the calculation, or you get almost a picture that shows you that these galaxies are embedded in halos of this mysterious dark matter.
Oh.
Now, dark matter reveals itself by its gravity. And so gravity behaves normally as far as dark matter is concerned, which suggests that if you had a dark matter black hole, it would exhibit its forces, or exhibit its presence in exactly the same way as a normal matter black hole does, because it would be a singularity with intense gravitational field around it, which would pull other stuff in, whether that was gas being accreted like it is at the center of a galaxy, whether it's a supermassive black hole, or an X-ray binary where you've got a companion star that's leaking material onto the black hole and causing it to release X-rays. All of that should still hold good, so that what you see in the black hole universe in real or normal matter, baryonic matter, you should also see in dark matter.
Right. Okay. Interesting. So probably not is what the answer is, which would have saved us a lot of time. But we were going slow at the start, so that's fine. I've actually discovered a white hole.
Where is it?
It's called my bank account. Nothing gets in.
Yes,
Nothing gets in.
But things get out.
Yeah.
Yes, that sounds like a white hole.
Yeah, it's definitely a white hole. All right. Thanks, Carlos. Let us move on to Duncan. I think Duncan sent us a few questions in recently, so let's tackle this particular one. I think he's looking at the period of inflation.
Hello, Duncan here from Weymouth in the UK. Question about the period of inflation after the Big Bang. When the universe expanded faster than the speed of light, was that faster than the actual speed of light, or was it that the speed of light at that time was faster than it was now? I'm just thinking that if the speed of light in itself at that time was faster, could it be that there is some property of the universe in which light is able to travel faster than what it does currently in the current vacuum? and that if we could discover what that particular property of the universe back then was, then maybe there would be some way that, obviously in the distant future, with our current technology, to create a drive that goes faster than it. I don't know. It's just that obviously we're limited to the speed of light, but if the speed of light in itself could be increased, then who knows? Anyway, thanks for your help. Keep up the good work. Bye.
Okay. Thank you, Duncan. Always good to hear from you. And now I understand how the Americans have learned to pronounce things differently to us because of Duncan's accent. I picked up an American pronunciation in there. I can't remember what the word was now. But
That's a pity.
yeah,
Because that's what I was going to ask you.
Yeah, I can't. It just went straight out of my head. It's very late on a Friday here, so my brain decides to give up once I've walked out of the office. But period of inflation, we know, immediately after the Big Bang, the universe expanded at faster than the speed of light, and then it slowed down, and now it's accelerating again. Where does Duncan's theory sit?
There's two different things we're talking about here, Andrew and Duncan. So when you think about inflation, the speed of light doesn't matter because it's the fabric of space, whatever that is. Yeah. It's it's space itself that's expanding, and you can only talk about being faster than the speed of light if you think of 2 points within that space. How fast are they receding from one another? And it may well be faster than the speed of light. In fact, it would have to be just because of the way the inflation took place. It was an extraordinary period in the universe's history. But it is the space that's expanding very fast, and that doesn't impact the speed of things going through it. So one of the basic foundations of cosmology, as we understand it, our theory of the origin and evolution of the universe, one of its basic principles is that the speed of light is a constant. Yeah. That it has always been the same. Ever since the beginning, it was 300,000 kilometers per second. There are probably still people, I haven't really caught up with this work yet, but, recently. I haven't caught up with it recently. This is work that was done a decade or more ago by colleagues here in Australia, in fact, principally at the University of New South Wales, who were observing different distant quasars. And there was just some evidence in those, there were spectra, they were taking the rainbow spectra of these quasars and looking at the features in them. There was evidence that hinted that something was varying, that one of the fundamental physics principles was different then than it is now. Because when you're looking at quasars, you're looking a long time back into the past. And the inference was that it was either the charge on the electron or the speed of light that was different. That work was always greeted with a reception that was less than warm by the astrophysical community. And I know why, because I've seen the data, and it was really it was right on the limit of detectability, this effect that they were highlighting. And I suspect that more recent observations, because we've now observed quasars to death in the last 20 years or so, I think with those more recent observations, it might have gone away. However, it might not have done. And I would not be surprised if we hear from one of the proponents of that work and one of the people who carried it out, who is a good friend. I'm going to tell the standard joke about this gentleman. I hope if he's listening, he won't mind. His name is John Webb. And the thing about John Webb was you never met up with him at the University of New South Wales. It was always in New York or Cambridge or Paris or somewhere. It was always somewhere else which is why he became known as the World Wide Web.
Ah, yes. I remember you telling me this once before. That's a great nickname.
Yeah.
Great nickname.
It is a great nickname. He's a great guy as well.
Yeah.
It'd be nice to try and catch up with him in Cairo or somewhere just to find out whether he's still, whether those ideas are still prevalent.
Yeah.
I should look it up.
I have a listener from Coonabarabran who emails me quite regularly and listens to Space Nuts. Hello, Barry. He sent me some nicknames the other day. Keth, Keth. It's the nickname of a bloke with named Keith, but he only has one eye. So he's lost his eye. Keth.
Okay.
I love it. That's a very clever nickname. Very clever nickname.
It is. It's a good one. Yeah, it's nearly as good as the guy with the shovel on his shoulder, isn't it?
What's that? Doug. Yeah. And the guy floating in the ocean, Bob.
Yes,
there's a
guy
million
without a shovel on his shoulder, Douglas.
Oh, we could go on forever, but we probably lose our entire audience.
See what you've done, Duncan?
Yes.
Just to return to it, I think, it really is very much a principle of our understanding of the universe that the speed of light hasn't varied. And so engineering the speed of light itself down the track is something that I suspect we would never get to.
Okay. And, not for want of trying, we're trying ways of speeding up our capacity to move through the universe, but getting to the speed of light. I mean, if we can get to a fraction of it, that'll be an achievement.
Yeah.
But full speed of light, probably way out of our realm, given how much energy is required. Thank you, Duncan. Loved the question. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, let us continue. And our next audio question comes from Mark.
Hi, guys. This is Mark from Baton Rouge, Louisiana. I really love your show. I understand that one of the lines of reasoning pointing toward the existence of dark matter has to do with the comparison of the rotational period of galaxies to the amount of matter that they contain. However, I've seen various estimates of the number of stars in the Milky Way galaxy, ranging anywhere from 100 to about 400 billion stars. This is quite a large error bar, I would say, and I'm curious how they can make this comparison if astronomers are this unsure of the number of stars in our own galaxy, much less other galaxies. Thanks, guys. I hope to get an answer.
We hope to give you one day. Actually, you're asking the right bloke, because Fred has been counting stars for all of his career.
Pretty well, that's right.
No.
And yes, the way you estimate the number of stars in a galaxy is certainly in our own galaxy. What you're trying to do is find a way of measuring its mass, and then you turn that into stellar masses. But one stellar mass does not necessarily equal one star.
Yeah.
So some of the work, in fact, I was involved with this work a decade or so ago, by trying to measure the mass of our galaxy by using the escape velocity of stars. If you think about the way some stars might escape from the galaxy, then you can use that. We did this with the RAVE experiment, the radial velocity experiment. You can actually deduce back what the mass of the galaxy is within that radius, where the particular star is. Actually, it's within the radius of the sun, the sun's distance from the center of the galaxy. And you get, if I remember rightly, we got 1.4 trillion solar masses for the mass of the galaxy, but that includes dark matter.
Right.
So it's not individual stars. So you've got to know something about the universe before you make these calculations. And looking at other galaxies, it's easier. We don't you don't count the individual stars in a galaxy. And it's only recently that we've been able to see the individual stars in a galaxy. Although back in the 1920s, Hubble was observing Cepheid variable stars in the Andromeda galaxy, and that was an early step in that direction. But most of the stars in a galaxy are too faint to do that, and all you see is this glow which collects them together. But by observing, so what you're doing is you're looking at the luminous characteristics of a galaxy, the stuff that is emitting light, even if you can't see the individual stars. And from that, you can deduce the stellar mass content that is emitting the light. In other words, you've got some handle on the normal matter. And it turns out that that is far too little to keep the galaxy held together. And so that difference between 100 and 400 stars in our 100 and 400 billion stars in our own galaxy, yes, it's a 4-to-1 error, but it's still well within the limits that would be imposed by dark matter. The dark matter itself is much more than that, is what I'm trying to say. It doesn't matter whether it's 100 billion or 400 billion, the dark matter content has to be still much more.
Okay.
So it's a good question, Mark, and goes to the heart of how we understand these things. It's not just the rotation of galaxies, of course, that leads us to believe dark matter is real. Another very strong pointer to the existence of dark matter is the distortion of space by clusters of galaxies and galaxies themselves. Once again, if you look at a galaxy, the space around it is distorted to the far more than you could account for simply by the luminous matter in the galaxy. It's got much more to it. And that's why we're so hooked on the idea of dark matter, because all the tests seem to suggest it's there.
Yeah. Wow. Okay. I've been trying to count the stars. I'm up to 5. So
you've been observing the Southern Cross then?
Yeah, that's as far as I got.
Yeah.
Oh, hang on. The sun. 6.
There you go. Very well done.
I'm making progress.
Yeah. Well done. You are.
Thank you, Mark. And now we've got a question from Nick, who is another sand groper. Do you know the term sand groper, Fred?
I don't, no.
That's what we call West Australians. They're sand gropers. So South Australians are crow eaters. I know where that comes from. Crow eaters because back in the day, during the gold rush, I think, or something around that era, there wasn't much food. So they used to eat crows. They used to shoot them. They called them something else. They called them desert pigeons or something. But they used to shoot crows and cook them and eat them. So they became crow eaters. I'm still to find out why a West Australian is called a sand groper, though. But I'm going to find out. I'm sure it's on the interwebs somewhere. Anyway, this sand groper is Nick from Perth, who has a question about planetary diversity. It is a given that the planets of our solar system formed by accretion from a disk of dust and gas circling around the young sun. That's the 6th star in the sky. Gravity-inspired differentiation leading to more dust on the inner disk and gas of the outer, resulting in the inner rocky planets and the outer gas giants. All good. Aside from those groupings, what fascinates me is the lack of homogeneity between the planets and moons around the gas giants within these two groupings. They are so different, all of them. How did that happen? Can Professor Watson recommend some reading on the matter? Should I buy his books? Well, the simple answer is yes, Nick. But it's an interesting observation, though, because we've got rocky planets inside, we've got gas giants further out, and yet they've got rocky moons surrounding them and ice moons and all this other weird stuff. Why is it so?
Yeah.
And which book is it in?
The best one, actually, is probably the kids' book. It's the one where I think I went into the most detail about planet formation, which I probably shouldn't have done in a kids' book, but never mind. It was fun to write. So we think we understand why there is this differentiation between the inner rocky planets and the outer gassy ones because of the existence of the frost line. So if you look at the distance from the sun, where water freezes, basically, it's kind of beyond. It's the outer edge of what you might call the outer edge of the Goldilocks zone. Where it's not too hot and it's not too cold for liquid water to exist. And so you've got, and it's between the orbits of Mars and Jupiter, basically, and that's what you'd expect, because we think that the idea of water, which is by far the commonest two-element molecule in the universe, freezing and causing an increase in the mass of the outer worlds as the planets were forming. We think that's why they were able to hold on to a gaseous envelope and become gas giants.
Yeah.
Whereas the inner rocky planets were within the frost line, and so it was, they weren't able to do that. So that's a neat explanation. But then the moons themselves, Nick is quite right that the moons themselves are diverse, but they are all basically rocky bodies, rather like asteroids, with some of them have got an overlayer of water and an overlayer of ice on top of that, many of them which we've talked about many times before. Some are just rock, like Io. Some are just lumps of, in fact, some are probably more like pumice. Phobos, the moon of Mars, is diverse in that regard, in that more than 50% of its mass is empty space.
Wow.
Which is what gives it that low density. So there is still diversity among the moons, even when you consider that, yes, they're all basically made of rock. But maybe the gas giants are as well. We don't know whether they have a rocky core.
Yes, that's one of the mysteries, isn't it? So it's possible the gas giants are something of an illusion in some respects.
Yes, that's right. They might be just rocky planets masquerading as something else.
Yeah, just got massive atmospheres.
Yeah, big atmosphere.
Yeah,
it's like a big hairdo, really.
Yes, which you don't know anything about, actually.
I did once.
Well, I'm rapidly catching up to you, as you can see. Yes. All right. Thank you, Nick, and enjoy groping the sand, whatever that means, in Western Australia. Love Western Australia. Beautiful, beautiful place. To our final question, Fred, and it comes from one of our favourite terraforming experts and sci-fi writers. I'm going to introduce him the way he introduces us. Hello, Martin.
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres. Today, we're going to terraform a completely theoretical object, and I would just like to know what you would see if you were on a Tipler cylinder and a circling around it overhead was a spaceship that Professor Tipler tells you would be going back in time. Love your show. Can't wait for the answer. Berman Gorvine in Potomac, Maryland, USA. Over and out.
Thank you, Martin. He's really stretching now, isn't he? Now, I just tried to look up what a Tipler cylinder is, also known as a Tipler time machine. It's a hypothetical object theorized to be a potential mode of time travel, although results have shown that a Tipler cylinder could only allow time travel if its length were infinite, with the existence of negative energy. So,
yeah, I'm actually looking at the same page as you,
right,
Andrew.
Yeah.
And it's if its length were infinite or with the existence of negative energy. So you've got two alternatives there.
Yeah,
and infinite length is tricky to make. Negative energy is even trickier. So that's why we're probably never going to build one. But what an interesting idea it was. It was it actually is something that falls out of the equations of relativity. And in fact, it was mathematicians looking at those equations back in the 1920s that produced this idea of, as you said, a hypothetical object theorized to be a potential mode of time travel. And it's because of its effect on the closure of space-time, if I can put it that way. The gravitational potential is such that you get, instead of space-time being a nice lattice of stuff, a bit like, I always think of space-time as being like one of those climbing frames that you find in kids' parks.
Oh,
which
yeah.
is the old-fashioned ones anyway. They're not like that anymore, but they were just a regular set of things arranged in right angles, and it gave you a three-dimensional structure. That's normal space-time. Bent space-time is when somebody heavy stands on one of those, and that's what the equations of relativity shows, that when you put matter in there, they bend. But when you think of all this happening around an infinitely long cylinder, you get the structure of space itself closes on itself, if I can put it that way, so that you've got a way of moving around in time as well as space. That's the idea. There's also a phenomenon called frame dragging, which we know is a real phenomenon of relativity. There was certain, I forgot which spacecraft it was. It won't come back to me. There was one particular spacecraft that was put into orbit around the Earth that was designed to demonstrate that the Earth, as it rotates, drags space-time with it.
Oh, yes.
This frame dragging phenomenon.
Yeah, we did.
So
I think we did a story on that a while back.
I think we did too. Yeah, I think we did too. And so the cylinder itself, if it's spinning along its long axis, will create this frame dragging effect, warping space-time in such a way that you might be able to travel backwards in time. That's the bottom line.
Okay.
And so I forgot what Martin's question was. What would a spacecraft look like that was going backwards in time? It'd probably be just like playing a movie in reverse.
Yeah,
really.
probably. Yeah.
Sadly, the boot was put in by a number of people, including a fellow called Stephen Hawking, and he threw a relativistic argument at the idea of a tipless cylinder, suggesting that it would never be able to be built.
Which means you couldn't terraform one, basically.
That's right. Forgotten terraforming was at the heart of Martin's question, as it always is.
Yeah.
And terraforming a tipless cylinder, yeah, that would be tricky.
That would be very tricky. Yeah. But, you're a sci-fi writer, Martin. Just do it.
Right.
Just do it. You can do anything in science fiction.
Well, that's the case, Andrew.
Yeah,
you do anything.
I'm currently reading the latest John Birmingham series. John's an English author, but he's Australian based, and he's just released. He always releases books in threes. All his stories have 3 volumes, and I'm in halfway through the second of 3 books in his latest series, and it's just a classic outer space war story, which is he hasn't done ones like that before. He's done other really interesting stories about monsters coming out of other dimensions and eating humans, and he did one about a big blob that came from outer space and wiped out half of America and half of Canada, and what happened to the world. That one was called Without America. He writes brilliantly, and I'm really enjoying this latest series, which he hasn't released the 3rd book yet, but it's due out this year. So I'm slowly reading the 2nd one so I can get straight into the 3rd one when it comes out. It's great stuff.
I once did a gig with him.
Oh, did you? Oh,
I
there
did
you are.
in Brisbane.
Yeah. He's I love his writing style, really do.
Yes.
My favourite character of his is Super Dave. Super Dave, yeah. And then that series has since been renamed the Super Dave series because it sort of took over.
So we've got to look out for the Super Dunk theory.
Oh, gosh.
Super Dunk series.
No.
If you're listening, John, this is it. Super Dunkley.
Yeah. Put in a kind word to your publishers for me. That'd be nice. That'll never happen. All right. Thank you very much, Martin. Always good to hear from you. We're going to wrap it up there, Fred. I think we got through a fair bit today. But again, I'll remind people, because we've now exhausted quite a few of our questions, to send them in via our website, spacenutspodcast.com. Click on the AMA link to send text or audio questions, or just click on the tab on the right-hand side of the homepage where you can send audio questions. Don't forget to tell us who you are and where you're from. You can record your questions via any device with a microphone. Basically, it's that simple. And check out all the other stuff on the website while you're there. Fred, thank you as always. It's a great pleasure. And it's good to get through some of the questions and hear from the audience.
Indeed, they talk far more sense than we do. Sounds great. Thanks, Andrew. I'll see you next time.
Indeed, we will. Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio who actually turned up for work today. And from me, Andrew Dunkley, catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.